This is Team 1052's presentation on Problem A by Daniel Warshofsky,
Alaguvalliappan Thiagarajan,
and Adam Kocsis. The problem asks us to model kleptotruchy in birds, which is a practice where birds steal hair from living animals to land their nests. Our goal is to see if the advantage of additional thermal insulation provided by the fur outweighs the risk of gathering the resource.
We chose the tufted titmouse as the species we are examining because they have been widely shown to practice kleptotruchy. Our research showed that the tufted titmouse have 6 to 12 eggs every year, and so we've chosen to assume that they lay 8 eggs per year or 2/3 eggs per month. Out of those eggs, there is about a 90% hatch rate under optimal conditions.
The model we decided to use is a variation of the logistic model. We chose the logistic model as a base because it can account for shared resources between populations without modeling them as predator and prey. In our model, we assume that the klepto birds and the normal bird populations do not mix. In our equations, N represents the population of the normal birds, K represents the population of the klepto birds, and C is the carrying capacity. The growth rates, which are the lambdas in our equation, are different from the standard logistic model because they vary with ambient temperature, which varies with time. So both lambdas are functions of time. To determine if kleptotruchy is a viable strategy, what we do is set our model with initial conditions such that both populations have equal starting amounts and let the model evolve. When the carrying capacity is reached, we see if the klepto birds have a larger population than the normal birds. If that's true, then we say that kleptotruchy is a viable strategy. If the normal birds have a higher population at that time, then we say kleptotruchy is not a viable strategy. In our model, we let the carrying capacity equal 100 so that N and K represent percentages of carrying capacity rather than total amount. In all, the only difference between the klepto birds and the normal birds are the growth rates lambda.
The growth rate lambda is determined by the birth rate minus the death rate. This value differs between the normal birds and the klepto birds. The birth rate is determined by the number of eggs laid times the proportion of which that hatch successfully. Since the fur the klepto birds snatch allows their eggs to have better insulation, the hatch rate will be higher, thereby increasing the relative birth rate. However, the practice of kleptotruchy increases the relative death rate because klepto birds can be killed while trying to snatch hair from mammals. 1/11 of the interactions where birds steal hair from mammals have the mammal posing aggressive behavior, and we've assumed that 1/10 of those interactions result in death. We've assumed that all other interactions that would cause death between the two birds are constant, so we've chosen to neglect them because we aim to compare the two populations relativistically, hence why the death rate for the normal population is 0. While we can see from the first table that there is a hatch rate of 89.25% at the optimal egg temperature of 99.5 degrees Fahrenheit, the hatch rate decreases when the temperature deviates from the optimal value. To determine the hatch rate at a given egg temperature, we linearly interpolated the values in the table. To get the egg temperature from the ambient temperature, we look at the graph on the right-hand side of the slide to see that the relationship can be modeled linearly. We assumed that the bird will always lay on the egg and that the temperature of the egg will be the temperature of the bird for the normal birds, but for the kleptobirds, their temperature will deviate from their parents' body temperature by the amount of insulation provided by the fur.
The equation we use for calculating thermal conductivity of the nest is theta equals negative mu times the difference between the temperature inside and outside of the nest, divided by the thickness of the insulating material. Mu is the thermal conductivity constant of fur, which is 0.0365 watts per meter Kelvin, and we assume the thickness of the fur is 1 centimeter. However, this value can be changed for subsequent runs of the simulations. For the uninsulated nest, we use the thermal conductivity of air, which is 0.025 watts per meter Kelvin. We gathered the temperature data from Rochester, New York, Nashville, Tennessee, and Savannah, Georgia, which are all homes to the tufted titmouse. These locations are marked on the leftmost map of the United States, and the middle graph shows the temperatures gathered throughout the year for the 3 locations. We use these locations since they are all in the geographic ranges inhabited by the tufted titmouse, as seen in the rightmost map, and have a wide range of temperatures. Graphing the heat conductivity function on some sample weather data, we see that the fur-lined nest loses no heat to the outside relative to a non-insulated nest, which would lose between 1.6 and 3.5 Fahrenheit of warmth, depending on the time of the year. While this is not a drastic variation in temperature, it can still decrease the hatch rate of non-insulated nests.
Here are the results of our simulation. Each graph represents a run of the simulation in a different climate. From left to right, we have Savannah, Georgia, then Nashville, Tennessee, and on the far right, Rochester, New York. On all of the graphs, the orange line represents the klepto population, the blue, the normal population, the green, the total population, and red, the temperature. In Savannah, Georgia, and Nashville, Tennessee, we see that the normal birds have a larger population at carrying capacity. Thus, in these 2 regions, we've determined that kleptotrichia is not a viable strategy. However, in Rochester, New York, we see that the klepto birds have a larger population at carrying capacity, so kleptotrichia is a viable strategy. In real life, we observe that the tufted titmouse still perform kleptotrichia in Nashville, Tennessee, and Savannah, Georgia. So there must be some other non-thermal benefit that kleptotrichia provides. Some benefits that it may provide are the warding off of predators. If there's mammal fur inside of the nest, predators may think that there is a large mammal nearby and stay away from that area. Having fur in the nest may be a status symbol amongst the birds, which may increase the rate of which they attract mates. Fur is not typically used in the construction of nests, so the fur may provide structural stability to the nest. Lastly, the fur may prevent bugs from getting to the nest, which can spread disease and kill eggs. In the future, we would like to update our model to be more realistic. To do this, we may want to include a predator to more accurately model the variations in the population. In our model, we have birds laying eggs at all times throughout the year. It's more realistic to have the birds lay most of their eggs during one time of the year. We may also use a more complex thermal modeling equation. And also, our model doesn't take into account the time it takes birds to reach sexual maturity. So including those into our model could make it more accurate. Thank you for listening to our presentation.